Okay, so I think I can start. It's already 10 minutes after 5 p.m. So, as you all know, I'm Sripan. I'm working as a PMRF at ITBHU and conducting this type of live session every week for 2 hours is one of my deliverables towards PMRF scheme. So, right now I am taking some live sessions for fluid dynamics for astrophysics, in which I am solving some sample problems, sample MCQs basically, which will be helpful for the students who are registered in the course uh, to solve the assignment problems given to them. And also it might be in general maybe useful for uh, every student who can or who want to know about the fluid dynamics more and more. So yeah, you all of you can are invited to see these lectures and live sessions and uh, enjoy yourself. Okay, so today is 18th of February and this is the third week of the live session. So today okay, so let me start with the first question. So here is 4 options or 4 statements. We need to check the incorrect statement. So first of all, we need to check the incorrect statement or the correct one. So Bernoulli's theorem is applicable irrespective of dissipation of certain type of energy, say kinetic energy, until the total energy associated with the flow is conserved. So if you remember the Bernoulli's theorem, it tells us that the total energy in the form of pressure head, kinetic energy head and the gravitational potential head, the sum of those three has to be constant, right? So the way we write it is half v square, which is per unit volume, right? Sorry, yeah, plus this is the pressure head dp by rho plus some phi. This should be a constant. Okay, now just a second. Okay, so Sumit, Shweta, welcome to the class. So I was discussing the first question, which is the choose the correct incorrect statement. So we have 4 statements. We need to find out which one of these are incorrect. So can you guys tell me the answers for it? I mean, let me decide first the options. So first one is telling that Bernoulli's theorem is applicable irrespective of dissipation of certain type of energy, say kinetic energy, which is, let's say this one, until the total energy associated with the flow is conserved. So if we know this equation, we can say that okay, until and unless this total energy amount is conserved, we can tell that that is Bernoulli theorem can be applicable to this flow, right? So if this is, let's say, half v square is changing, it might be transformed to other forms of the energy. So the total energy is conserved for the Bernoulli equation. Now tell me with the other 3 options, which one of those are incorrect. So first one is correct, so it cannot be our answer. Now we have viscosity will produce circulation in fluids. So is it true? I mean, what do you mean by viscosity is, let's say we have this kind of some layers and every layer has some velocity and there is a gradient in the velocity. Let's say this is v plus dv, this is b. So you have a gradient in this direction, right? Let's say this is y. So you have dv dy, which is not equals to 0. Now whether this gradient can produce some circulation in fluids. Sumit, what do you think?
This will produce circulation. So second
Okay.
is correct.
So this one is correct. Okay. Now Bernoulli's theorem is not applicable if curl of u is not equals to 0. So first of all, what do we mean by curl of u equals to 0 is the irrotational flow, right? Now if it is not equals to 0, whether Bernoulli's theorem will be applicable or not. Can anyone tell me? Sumit, Shweta.
I think 3 is incorrect.
Okay, so Bernoulli's theorem is basically applicable irrespective of this curl of u, right?
Yes,
Yeah.
correct.
So yeah, this is one of the option. Now for a fluid, both velocity potential and stream function obey Laplace equation. So what the question is suggesting is, let's say you have grad phi equals to 0 and another is the stream function which is grad psi equals to 0. Now the fluid will stick in the solid surface, whether it is correct or not.
This is incorrect.
So
It should
fluid will stick only if there is some
viscosity.
So yeah,
Yes.
for this it cannot be correct. So these two options are incorrect statements. Who else is in the class? Shweta. Did you get it, Shweta? Any problem? Hello.
Yes, sir.
So any issue with from your side? I think you understand, right? Or is it too fast?
Okay, sir.
Okay. Okay. So the next question is here. So turbulence problems particularly depends on this term of the Navier-Stokes equation. Now, first of all, we need to recall what is the Navier-Stokes equations form, right? So, if we try to write down the Navier-Stokes equation, we have rho del v del t plus what rho v dot grad, this is dot v equals to, when we write the Euler equation, we are just considering only the pressure gradient and the force due to gravitational pull. Now when we go to Navier-Stokes equation, what else we consider except these two, Sumit?
This is viscosity.
Now for viscosity we have additional term which is mu grad square v, right? Yes. So this is the additional term. Now when we consider the in viscid fluid, we also tell that there is some irrotationality also there, so that cannot have any turbulence, right? Now when we add this, the fluid can have some turbulence. Now the turbulence is coming from this term, right? If it is not there, there is no turbulence, correct? So now this is the cause of turbulence. Now what it does, so if we remember the diffusion equation, so what the diffusion equation tells is, let's say some properties like there, right? Del rho del t can be eta grad square some function of that, right? Let's say rho or something. So this way a diffusion equation is written. Now if we compare this equation with this, so you see that if these terms are not there, this is basically the diffusion equation, you know. So what this viscous term is doing is, it is a diffusion term in this equation. Now we have these four options. So first of all, rate of change, how the turbulence problem is depending on which term. Okay, so first option is rate of change term. So turbulence problem will depend on rate of change term because it increases in internal energy. So here you see this is the rate of change term, this del V del T. So this is not going to increase your internal energy at any cost, right? It does not have any dependency or any connection with the internal energy. The second thing is convection term, as it increases enthalpy. So that is also not true. Now the third term is diffusion term, as it increases entropy. So we have a diffusion term, okay, but how do we know the entropy is increasing? Now entropy depends upon the degree of disorderedness, right? So when there is some turbulence, we have less ordering of the flow, correct? So we have the diffusion term in the form of viscosity, which will increase the entropy, and that means there is some turbulence. So I think this third this third option is correct. Okay, so Sumit, any issue?
No issue. I'm still trying to understand the question. The question says turbulence depends on this term of the Navier-Stokes.
Yeah, so Navier-Stokes equation have this rate of change term also, right?
Yes,
So
yes,
there
correct.
are lots of terms in the Navier-Stokes equation. So
Mhm.
which term is basically responsible for the turbulence? Okay.
Okay.
Yeah.
Yes,
So
correct.
why which term and why it is responsible? So that is the question asking.
Okay. I
Yeah.
got it. Yeah. Now I understood the answer.
Okay. Shweta, any issue?
Shweta left. She's not there.
Okay. So you were only alone, right?
It looks like yes.
Okay. Fine. Okay, just tell me one thing. The lecture videos are shared with you guys or not? The last
Give me
2
a
weeks? Yes.
I did not see any announcement. Maybe it's there on the portal. Give me a second. I'll check and let you back. Give me a
Yeah,
second.
please.
No, I don't see the tutorial videos yet on the portal.
Okay, fine. I think they are missing something because I already shared with them everything. I don't know why they are
I see
not.
only one problem solving session video.
Uh,
Okay. I think there is a different drive folder that they have shared. Oh yes. I see the two YouTube link is given in that
okay,
sheet. It's not there. Okay,
okay,
it's there.
okay, fine then. Okay, fine. So, okay, let's move on to the next question. So, we have a man is applying water to a newly made wall to strengthen it via laminar flow through a horizontal cylindrical pipe. So let's say you have a wall like this, a vertical wall, and you have a pipe. So a man is giving water to the wall via this pipe. So the flow is laminar. Okay, so there is no turbulence initially. Now the water on imparting, so the imparting basically imparting on the wall is subjected to turbulence. Is it violation of conservation of circulation? So first of all, what do you know is there is a theorem, like if the circulation is conserved at for some inviscid fluid, then it has to be conserved, or sorry, if the circulation is given at a certain time, then if it is the inviscid fluid, the circulation or the amount of circulation will conserve throughout the time of the flow. right? So now it is asking that now the water on imparting on the wall is subjected to turbulence. So first of all, while it is having a laminar flow, so that should not have any circulation associated with it. But as soon as it is imparting on the wall, it is subjected to some turbulence. That means there is some circulation is present there, but initially there is no circulation. So something is created from nothing, right? So whether this is the violation of the conservation of circulation what we studied. If it is yes, why? If it is no, why? So can you tell me, Sumit, that
This is not a violation of conservation of circulation because
because
the theorem is based on the fact on an assumption that there is no viscosity related, that the fluid is inviscid in nature.
mm-hmm.
But then what happens is when the water is there on the wall,
Mm-hmm.
it suddenly comes to a stop,
Mm-hmm.
and because of that the gradient, the velocity gradient is very very high
Mm-hmm.
at the surface of the wall.
Yeah.
And because the gradient is very very high, then the mu del square mu into del square v, that is a viscosity term in the Navier-Stokes equation also, it becomes important.
Yeah.
And when it becomes important, the assumption breaks down. So it is no longer inviscid flow. There is some viscosity there. I mean, there is an effect of viscosity, and that's why
Yeah.
vortices are seen there.
So basically what happens is this if it is considered as a bulk flow, so as a bulk there is no viscosity, but by viscosity I mean there is no there is very small viscous coefficient which is given by mu, right? Now it is going with some velocity, let's say u, and it comes to a stop at this, let's say you have a 0 here. So you, as you said, that there is a very steep gradient of the velocity, and as the viscosity depends upon two terms. One is the viscosity coefficient, another is the grad square u. Now this going to be a big have a big value at this region. So that gives you this mu grad square u is going to be significant. So this is no longer a inviscid fluid in that local region. So okay, significant. Okay, so yeah, so that's how so the conservation of circulation is not violated at all, because the regime in which we are telling is the viscous regime, in which the conservation of circulation is not applicable at all. Okay, so yeah, so okay. Now let's move on to the next question slide. So it's about the Magnus effect. So the question is saying that Yadvendra Chahal was a slow flighted stator delivery to Martin Guptill, which he launches for 6. So first of all he gives some flight, some air to the ball. Now next ball, Chahal balls a quick spin, and Guptill is led to react to the quicker dip of the ball compared to the last ball and gets bowled. So why? So Sumit, can you answer it?
Yes. So in the next ball, Chahal, when he balls this, then he gives some initial spin to the ball.
Yeah.
And as a spin to the ball, due to the spin action, the ball experiences a downward force.
Yeah.
And because of that, it goes down and
Yes.
deceives the batsman. So that is the reasoning I can come up with.
Okay. So basically, what happens is, so in cricket, whatever is going on, let's say ball is going on through air. Now air is a fluid, whatever small is the viscosity, there is some amount of viscosity, right? So as he spin the ball, right? So a leg spinner, so what he is doing is he is giving some circulation in this direction, right? The like this direction. So if it is in this direction and it is going through some air, right? So what happens is somewhere, let's say this is the air flow, okay? So if it is air flow, so what happens, the in the above region there is a subtraction of velocity because they are oppositely directed, and in this there is a addition, right? Addition of v. So what happens is here there is a larger v, there is a smaller v, and let's say this is a capital V. Now here Bernoulli theorem is also applicable, right? So if we have to apply the Bernoulli theorem, what we know is half capital V square, let's say this is capital P in this region, the below region, and we have half V square plus in this region there is a smaller p, let's say. So what will happen, if v is greater than small v, then obviously this p should be less than small p, right? Now you have a high pressure region on the above of the ball, and in the below there is a low pressure region. So what will happen, there is a downward force due to this pressure gradient which will give a dip to the ball as it approaches the batsman. So it will dip more than the expectation of the batter. So that's how he can be late to react to the quicker dip. Okay, here another mistake is here. So this is not late. Okay, so Sumit, you are absolutely correct about this, but still I have to. Okay. Just a second. Okay, so the next question is that one horizontal pipe of length 10 meter is connected from a water tank to a small container. So what we have is a horizontal pipe like this, and you have a large water tank here, and you have a small can here. Okay, so through the pipe water is flowing like this. Water flow is there from the tank to the can, and water has density of 1 gram per semi-cube. It started to flow through the pipe with a velocity of 5.6 meter per second and finally filling up the container. Now similarly, you have glycerin of some density which is higher than water density is flowing through the another pipe of same dimension. So in each case the dimension of the pipe is same with a velocity of 5 meter per second and filling up another similar container. So which one of this flow will impart more pressure on the wall of the small container? So first of all, how this pressure is generated? So pressure is coming from the momentum what has been carried by the flow, right? Now the momentum is directly connected to this half rho v square, correct? Now we need to find out that this half rho v square what has been carried by these two, one is water, another is glycerin, which one is greater, so that also gives us the more pressure, right? But here is another catch. So basically what happens is, due to some viscosity, there can be some dissipation of the kinetic energy, as we already know. Now water has some viscosity and glycerin has some viscosity, but the glycerin has more viscous coefficient, or glycerin is more viscous than water. So even if let's say glycerin has initially higher kinetic energy, so it can happen that depending upon the total initial kinetic energy as well as the viscosity, we cannot surely predict that glycerin, even though it will have a greater half rho v square, it cannot impart more pressure on the wall with respect to water. Okay, it also depends upon one other thing, which is the viscous coefficient. So both of these things has to consider. So first of all, what we need to do is, we need to calculate this half rho v square for water as well as the glycerin. So Sumit, can you do it for me, or yourself also, that half rho v square? I think the
Yes.
discussion is understandable.
Yes, yes, I can
Yeah,
understand.
so first of all, do this half rho v square and check whether there is any difference in between them, or uh, that's it.
Yes. Five meters per second. They are almost very similar. One is 15.68, the other is 15.62.
Okay, now they are similar. Now the question is about the viscosity, right? Because that will dissipate some amount of this kinetic energy. Now glycerin has a higher viscosity than the water, so that amount of dissipation of this energy will be higher in the glycerin case, right?
Yes.
So less amount of kinetic energy will be carried through the to the small container, so that will give us less pressure for the glycerin than the water. Okay,
Yes, correct.
so that's the answer for this, that for both there is similar. Okay, so first of all, we need to calculate the kinetic energy density, and it will come out to be same in both cases in this question. Now since both water and glycerin are viscous fluid, there must be some dissipation of the initial kinetic energy before imparting on the wall of the container. Now since glycerin has higher viscosity, amount of dissipation will be higher, and hence the final kinetic energy or momentum will be smaller than water. So yeah, now let's move on to the next question. So it is telling that it is noticed that dust are sticked in the planes of ceiling as well as table fans. So can we consider it as an observational evidence of air as an inviscid fluid? So this is pretty straightforward question, not very difficult. So Sumit, please answer. So we all see that in our household, we see that there is some dust which is sticked on the ceiling fans or table fans, right? So how this can we consider it as some observational evidence of air as an inviscid fluid? So first of all, the question relies on this fact that whenever there is some sticking, that sticking is coming from the viscosity, right? So if there is some evidence, basically really that is of the air as a viscous fluid rather than inviscid fluid, correct? If it is inviscid fluid, there should not be any sticking of the dust in the planes of the ceiling fans or table fans, correct? So it should not be considered as an observational evidence of air as an inviscid fluid, rather it is the observational evidence of air as viscous fluid, correct? Sumit, any point? Hello, are you there? Okay, so okay, now what we have is, so this is the answer to this question. Okay, so first of all, for inviscid fluid there is possibility of slip or finite tangential velocity of the air in closest distance with the solid surface in the form of fan plane. Here in this question the solid surface is fan plane, as there is no such property as sticking, correct? Now if there is no viscosity, there is possibility of slip, so the air will be just slipping with some finite tangential velocity, right? It should not stick at the fan plane. Now rather, while the medium is viscous in nature, it gives no slip condition. That means the normal velocity for inviscid fluid also, the normal velocity means the velocity normal to the solid surface, that is already considered as the zero. But in case of viscous fluid, we also consider that the tangential velocity will also be zero. Now in that case, the air, or more specifically the dust carried by the air, can easily get stick to the fan plane. So it is basically an observational evidence of air as viscous fluid rather than inviscid fluid. Okay, Shumit, are you back?
Yes, I just rejoined.
Okay, fine. So I think it's clear, right? This one.
Yes, correct.
Yes, easy. Okay. Now we have some numerical problem here. So we have a horizontal jet of fluid which is spread on a circular plate of diameter 6 meter. The density of the fluid is 2000 kg per meter cube. Speed of the fluid when it hits the plate is 10 meter per second. Now the force needed to hold the plate stationary is, so what will be the force? So first of all we need to understand that since this horizontal jet of fluid is spread on the circular plate of some diameter, so it will give some impulse or force to the circular plate. Now if we need to hold the plate stationary, that means we have to impart the same amount of force just opposite to the force already applied to the plate, so that the net force on the plate is going to be 0, and that is the necessary condition for the stationarity, correct? So first of all, what we need to do is to calculate the force given to the plate by this horizontal jet of fluid. Okay, now to calculate the force, what we can do, we have this parameters, correct? We have rho, which is given as kg per meter cube, correct? And we have v, which is 10 meter per second. Okay, and the other thing is there is a diameter called the plate diameter, which is 6 meter, right? Now what it tells is, if we remember the Bernoulli equation, we have this pressure term, right, plus half rho v square, right? Now if we add two quantities, that means the dimensionality will be same, right? So this half rho v square will have a dimension of pressure only, right? Now from pressure, how can we find out the force? Is the pressure is basically A by A, right? The area of the plate need to be considered. Now if we need to find out the force, what we need to do is, instead of pressure, we have to calculate this half rho v square here, half rho v square into, there is a circular plate, so the radius, area will be pi r square. Now we have been given as d, the diameter, so we have to put these values of half into 10 square, right? This v into, there is pi 4, correct, into, there is a d is 6, that should be 36, right? So if we cancel out this one, so this should be a 9. So you can find out there is a 9 pi into 10 cube, because this is 1000 and 10 to the power 4, sorry, 100, sorry, this is 100. So this is basically 10 to the power 5 Newton. Okay, Sumit, can you calculate it and tell me which one is correct?
Yeah, it is number 4, 2.83.
Okay,
10 to the power 6.
so the process is clear, right?
Yes.
Okay, so this is 2.83, it will come as 2.83. Okay, now fine. The next question is this one. So okay, when the term mu grad square u is present in the momentum equation, it means that the fluid described by this equation will stick to the surface of a solid body immersed in it. It will not stick in the second, and the fluid is irrotational. A small paddle wheel placed in the interior of the fluid flow will not rotate, and it will rotate. So which are the correct options for this question?
A and D.
A and D. So basically, if it is present there, this mu grad square u, that means you have the viscosity present there. So if it is viscous fluid, then there will be sticking. So this is correct. And another is, if there is the viscosity, that means there is some irrotationality. Sorry, there is some rotationality, correct? So this is rotational, and when the fluid is rotational, so basically the paddle wheel must be rotating, right? Because the fluid is imparting some rotation on the paddle wheel. So A and D, both of them will be correct answer for this. Okay, so the next question is this one. Now you have 1 mole of inviscid monoatomic ideal gas. Calculate its internal energy per unit mass. So can you do it? You have an ideal gas which is monoatomic in nature, and 1 mole there is a 1 mole, and also it is inviscid. Okay, now you need to calculate the internal energy per unit mass or specific internal energy. Fine.
I think the answer is 2.5 p by rho. Okay, p by rho is so it is number 1.
P by 2.5. Why this is 2.5?
I have the calculation. Wait, I'll find out. This was there in the assignment. Wait, I'll tell you. Where is it?
I think in the assignment there is the specific enthalpy is there, but this is asking for internal energy.
So are not they the same thing?
No.
Enthalpy? No.
No.
Okay. Then wait. Give me a second. Let me try it out. I need some help on this.
Okay. So basically, when you write that enthalpy equation, let's say you have the enthalpy as H. So what you write is there is a P, right? Gamma minus 1 rho plus P by rho, right? This way the enthalpy has been written, correct?
Yes.
Now basically this first term, this is your internal energy per mass. This is specific internal energy. Okay. So what you just to have to do is this calculate just this term, not the total thing. So now you have a monoatomic gas. So for monoatomic gas, what we have is the gamma is 5 by 3, right?
Yes.
So can you tell me how this 5 by 3 is coming?
I don't remember that. I just know this thing. 5 by 3 is for monoatomic, for diatomic 7 by 2, something like this.
Okay. So can you know about the degree of freedom?
Yes.
Okay.
Correct. Yeah, I know.
Now let's say you have a container like this, or a free space in which you have monoatomic gases, correct? Now if you have monoatomic gases and you don't have any constant, so this is a 3-dimensional space, correct? So the dimension is 3. Okay. Now if it is dimension is 3, then there is a formula like gamma is 1 plus 2 by F. Okay, where F is the degree of freedom. Now you don't have any constant. A particular, if you consider a particular gas molecule, it can go in any direction, right? So it is a x. If it is a x, y and z space, then you have to specify these 3, right? There is no there is no equation or constant which can give you a dependency between which can give a dependency between x, y, z. So they are free and independent of each other. Okay. Now the degree of freedom is the number of the independent coordinates. So here you have 3 independent coordinates, correct? So you have 1 plus 2 by 3 because you have 3 independent coordinates. Okay. Sumit?
Yes, I'm following that one.
Yeah, so this is 5 by 3. Now if you have, let's say, diatomic gas, so what happens is, so there is a bond between two atoms of a particular two molecules of a particular gas, correct? So then there is a bond length in between them, and however they are going in several direction, it is also a three-dimensional space. So for each there is 3 degree of freedom if we don't consider this bond length to be constant. Okay, so what happens is this bond length is not going to change. Fine. So if it is has x1 y1 and z1, and if it is, let's say, x2 y2 and z2, now x1 y1 z1 is also changing with time as it is moving in different directions, and also x2 y2 z2 is changing also with time. But what happens is this x2 minus x1 whole square, basically the length between these two, right? So this is y2 minus y1 whole square plus z2 minus z1 whole square. This should be the length of this bond, right? Let's say L square. So there is a equation in this case for diatomic gas which gives Z if you know x and y. Okay, so you have basically, without this bond length, you have 6 coordinates, right? So for each particle you have 3 coordinates, so you have 6 coordinates, but you have one constant equation which can give rise to a lesser number of independent coordinates. Okay, so this will give you a 5. Fine.
Yes, correct.
Yeah. So now if we consider this gamma for this will be 1 by 1 plus 2 by 5, and that will give you
7 by 5.
7 by 5. Okay, so this way these things are coming.
Okay.
Yeah. Now instead of this monoatomic, the question can ask for diatomic, even triatomic. So this way you can calculate for triatomic also. So that's how you can have this answer. Okay.
Okay.
Now now if we calculate this 1.5, so we may get this p by rho is m. So basically you have m by gamma is for here is 5 by 3 minus 1. So this is basically how 3 by 2 m, correct? So this is this 1.5 m. Okay.
Okay, I got it. Yeah.
Now okay, let's the next question, and the last question for this week is this one. So you have now
I have just one question on the last question that we had. So I understand enthalpy and internal energy, they are both energy, right? Both have dimensions of energy, right? So I'm just confused. For the internal energy, I'm getting 1.5 m,
Mm-hmm.
But in the assignment, the correct answer was 5 by 2m. Sorry, 5 by 2, yeah, 5 by 2m.
Yes, but there was a p by rho, another term is there, right? When you consider enthalpy, you have to consider
Okay,
both
okay.
these terms. But
Okay, okay,
here
okay,
you are
got it.
considering only internal energy term. So this is the first term. So if you have like this is 1.5 m and this is 1 m, right? So
Yes.
that will add up to 2.5 m when you
Okay, okay,
consider the
okay.
enthalpy.
Okay,
Yeah.
got it.
Now to the next question is now instead of monoatomic molecule, you have a triatomic molecule, right? Consider 1 mole of CO2. So you have 1 carbon and 2 oxygen. So in which a sphere is inserted. Now the sphere is not subjected to any kind of rotation. Okay. Now here the question is just a little bit tricky, but not that much tricky. So in the last question, you see the gas is inviscid in nature, right? Now here the question is telling that if we insert a sphere within this gas container, the sphere is not subjected to any kind of rotation. So that means the fluid which we are considering is not irrotational, and that means there is no viscosity associated with this, right? Again, this is the inviscid fluid, correct, Sumit?
Yes,
This is
yes.
also
Inviscid.
inviscid. Okay. Now, also convince yourself that the gas is in ideal state. This is pretty similar uh, to the last question. Now you have the calculate its enthalpy per unit mass. What they have given in uh, the assignment is this enthalpy per unit mass, but there that was a monoatomic gas. Now, as I discussed in the last slide, that we have how to derive that gamma for different atoms or different gases like monatomic, diatomic, triatomic. Now here you have a triatomic gas which is also linear in nature, right? So whenever we have a CO2, what will happen is this is some bonds, right? Like this, correct? This is its bond structure for CO2. There is a C in between and OR in the sidewise, correct? Now you see here you have two bonds, right? Here is a length which has to be unchanged, and here is a length which has to be unchanged. So you have two constants, correct? And in general, what happens is the space is 3D space and you have three molecules. So for each molecule, now forget about this constant first of all, you have three molecules. For each molecule you have three coordinates, so you have total 3 into 3, 9 coordinates. Okay, now you have two constants, that means the number of independent coordinates will be reduced by 2. Now this will give you 9 minus 2 is 7. Okay, now if we look back to this gamma formula, what we will get 1 plus 2 by 7. Okay, so that will give you 9 by 7. Fine. Now you know the enthalpy formula, which is P by gamma minus 1 rho plus P by rho. Fine. Now you have to put this value and also take this m. So you have 1 by gamma minus 1 plus 1 by gamma minus 1 plus 1. So you have m gamma minus 1 plus 1. So this is gamma, right? Gamma by gamma minus. Okay, now if we put this 9 by 7 here, you have this 9 by 7 by 9 by 7 minus 1. Okay, so you will find out what 9 by 2m, okay, which is 4.5 m. Okay, I think you got it.
Yes.
Yeah, so this is 4.5. So depending upon the structure of the molecule, the gamma will change, and how it is changed, that is discussed. Now I think you don't have any problem for how these gammas are coming. Now,
Yes.
now you don't need to remember these things. You can
Yes.
calculate by
Yes.
yourself.
Correct.
Okay, so I think that's all for today. uh, I hope so. There is just one student in, just you are there, so I think this is fine. So they are also uploading now. I think this number of student is will be decreasing day by day, so it's fine. Okay, and so this assignment has been the submission date at 15, right? This third one.
Third. Yes. Third assignment was 15th.
So I was conducting the session after the submission of the assignment, and that can be also a reason, but I don't know how this paper is conducting this time. Okay, so that's all. um
I
yeah.
had a concern with one of the assignment questions. I raised it in the discussion, but then there was no response.
Which one?
So, can I discuss that with you? I did not have the answer right now. It is related to week two. Yeah, assignment two.
Uh-huh.
For the assignment on week two, and the question number is two. The Boussinesq approximation is related to. There are four options: mass conservation, energy conservation, incompressibility, and last option is situations where one can neglect the density variations in the rho g term. Correct.
Okay.
Uh, so my understanding is in the Boussinesq approximation, one cannot neglect the rho g variation. Correct. That is my understanding. I might be wrong, but then that is given as a correct option in the assignment answers. So I am still a bit confused because in the notes it says in the Boussinesq approximation you cannot neglect density variations rho g, but in the answer sheet it is checked as one of the correct answers.
See,
So
whenever you are considering about some variation in some quantity, that should have some special scale associated with it. Okay, so
okay,
let's say you have a special scale of 5 meter, and the density is changing in a scale, changing by considerable amount in a scale of 10 meter. Okay, 10 or 50, 100 meter. Now
okay,
if we consider that 5 meter length scale only, you cannot find out any change in the density, correct? So you
okay,
have a higher length scale in which the density is changing. Now you have a low length scale in which you are considering the dynamics. So you don't have that information of the variation of the density in that smaller length scale, because it is changing at a higher length scale, correct?
okay, okay.
So it also depends upon this length scale problem. That's why this question is asking that about the gravitational scale height, right? So gravitational scale height is basically that length scale over which your density or your pressure that falls up by 1 by e times of its initial value, right? So so that gives you a characteristic length scale over which it has a considerable amount of variation. Now if you have a very small length scale considered respect to the gravitational scale height, then you cannot find any variation in the density. Now in those case, you can consider the density to be homogeneous. Okay,
Okay, okay,
but if you have a length scale which is greater than that length, that particular length scale over which the density is changing, then you may find some inhomogeneity or some variation in your density profile in the entire space. So it's all about the length scale over which you are considering your dynamics. Fine.
Yes.
Yeah. So
Okay.
Bosenius
Okay.
condition also depends upon this length scale also.
Length scale.
This
Okay.
does
Okay.
not depend upon only this rho g term and everything. It has something to do with this length scale. So that's why there is that option like gravitational scale height.
Okay. Okay. Got it. Got it.
Yeah. So okay. I also have the content for fourth week, but I don't know. I mean, just one. You are only joining. Should I discuss? I was thinking that someone is telling that day because we are running late by some days. So I thought if people were there, I think I can discuss that also. But I don't know what I can do. So, what do you think?
I am okay to discuss. The time is till 7 o'clock, so I am available.